All right, welcome back. So here's 5.3 tests for Extrema. So we talked about the critical points last time in 5.2. 5.3 is now verifying whether those critical points are minimums or maximums or neither. And there's two tests to do this. The first one is called the first derivative test. So again, we have our critical point C. The function is continuous in this interval. It's differentiable in this interval. So except possibly at C again, C does not have to be differentiable. That's like our sharp turning point for the V for the absolute value function. But either way, the function is continuous, differentiable everywhere except possibly at C. If the derivative goes from negative to positive, it's a minimum. Which again, when you think about it, makes sense. The derivative being negative means we are decreasing and then we're increasing. F prime is negative there, it's positive there. Well, that clearly creates a minimum location. And then if it goes from positive to negative, that's going to create a maximum. Again, makes sense. If we're going from positive to negative, we are increasing. That's where the derivative is positive. And then we go to decreasing, that's where the derivative is negative. So again, that clearly creates a max. And if it doesn't change, it goes positive to positive or negative to negative, then it's neither min nor max. You'll find that would occur with something like f of x equals x cubed, because that derivative is 3x squared, which means the critical point is at 0. But you can see when you look at the x cubed graph, there is no minimum there at 0, which is increasing, kind of flat lines, and then goes back to increasing afterwards. So that's what's kind of happening with option 3 there. So the idea here is we're going to find our critical points, and then we're going to use this first derivative test, see what happens to the change of signs. So we'll start off with a polynomial equation. So we're going to go ahead and take our derivative. We get negative 4x cubed minus 3x squared plus 6x. We set that equal to 0. We can factor out a negative x to get 4x squared minus 3x plus 6. I'm sorry, plus 3x minus 6. Why a negative x? Well, the x they all have in common, and I generally don't like having a negative coefficient for a quadratic for the leading term. Now, 4x squared plus 3x minus 6 is not going to factor, so we're going to go ahead and use our calculator. So when we solve the negative x equals 0, we just get x equals 0. And when we solve 4x squared plus 3x minus 6 equals 0, we just set that in our calculator. We graph that equation, and we find our two intercepts, which are going to occur at negative 1.6559, and again at positive 0.9059. So those are our three critical point locations, so they could be minimums and maximums, and which ones are they? So what we're going to do is we're going to set up a interval chart. So we're going to have our interval, we're going to have a test value, and then we're going to get the sign for that value. So our first interval goes from negative infinity to the first critical point, which would be negative 1.6559. The next interval goes from that critical point, 1.6559, to the next one, which is 0. And then we go 0 to 0.9059, and then 0.9059 on to positive infinity. So we're going to test a number like negative 2, a nice simple number that falls in that interval, negative infinity to negative 1.6559, a negative 1 here, 0.5, and then a positive 1 here. And we're looking to see what is our derivative value sign. So we're plugging this back into negative 4x cubed minus 3x squared plus 6x. It's very important if you do something by like dividing out a number to your derivative to solve the equation, you go back to the very original, because if you divide out a negative number, you're changing the sign value by doing that. So always go back to the original after the derivative to plug into that. If it's like a fully factored thing, then you can plug back into that also. So you're going to find if you plug in negative 2 into the derivative, f prime and negative 2, you'd have negative 4 times negative 2 cubed minus 3 times negative 2 squared plus 6 times negative 2. You're going to get a positive value. You substitute a negative 1, you're going to get a negative value. Positive 0.5, you're going to get a positive value. And then positive 1, you're going to get a negative value. In general, you should see that it should always be an alternating sign for these things, plus, minus, plus, minus. It's not going to always be like that. There are certain locations possibly where the derivative is undefined, where a critical point could exist. That might cause it to not alternate. More importantly, if it had been like, x squared we factored out, a double root, then it's generally not going to change signs at that location. All right, so we can see at negative 1.6559, it went from positive to negative. It went from increasing to decreasing, which means this is a maximum. At 0, it went from negative to positive, which means it went from decreasing to increasing, so that's a minimum. And then at positive 0.9059, it went from increasing to decreasing. That's a maximum. If they want the actual coordinate point, then you would just take these numbers and plug them back into the original. Plugging in 0 gives us 0, so there's a minimum at 0, 0. And then you'd plug in the 2 decimal values into the original, get some decimal value for that, and that would again be 2 maximum point locations. All right, so this is how you find the max and mins using calculus rather than just graphing the whole thing and seeing where a max and min occurs. Let's do another one. So this one we have x e to the 5x. So again, we're taking our derivative, which is going to be a product rule. There's our first function, there's our second. So f prime of x would be derivative x is 1 times e to the 5x, plus we leave x alone, derivative e to the 5x is 5e to the 5x, which we can't combine anything, but we can factor e to the 5x out, leaving 1 plus 5x on the inside. And we set that equal to 0. So e to the 5x equals 0, 1 plus 5x equals 0. Exponentials, unless they're multiplying by a number or adding or subtracting a number at the end, but by itself, exponentials can only be a positive value. Can't be negative, can't even be 0. So this doesn't solve. Whereas the other one does solve, and we'll get x equals negative 1/5. So there's only one critical point location. So when we do our test interval, our chart, we're only doing 2 intervals. So interval, test, and sign. So our interval will go negative infinity to a negative 1/5, and then negative 1/5 onto positive infinity. And we would test negative 1 and 0, probably the 2 best ones. Now, e to the 5x is always going to be a positive value, no matter what we plug in for x. So that part almost doesn't matter in this case. We're only really caring about what's happening to the 1 plus 5x. And that's the kind of logic you want to use if you're not allowed to use a calculator for this kind of question, which is entirely possible. If you're doing something like AP Calculus, this could easily be a non-calculator-based question because as long as you recognize e to the 5x is always positive, it's just a linear you're worrying about. Plugging negative 1 into 1 plus 5x gets you a negative 4, so it's a negative there. Whereas plugging in 0 gives you a positive 1, so it's a positive there. And again, if we're going from negative to positive, we're going from decreasing to increasing, this is going to be a minimum. All right, now you can do this with all sorts of different types of functions. We're going to keep on exploring other types of f of x equations, solving them out, and everything else. But that's the idea behind the first derivative test. Take the derivative, set equal to 0, solve that, and then use test intervals to see whether or not it's negative or positive, things are changing or not. Now, if you're given a graph, a little bit easier. So they tell us this is the graph of the derivative. So they want to find all max and min points of f of x. Now, for a derivative graph, again, the max and min occurs. We're looking for when f prime of x is equal to 0. Where is that happening? Well, here at negative 2, here at 0, and here at positive 2. Those are your 3 critical point locations. Not the max and mins physically in the graph. That would be if we were given the graph of the function, not the graph of the derivative. Graph of the derivative, you're looking for where do we cross the x-axis. So we can see before negative 2, we're above it, so that means it's a positive value of f prime. After negative 2 and before 0, it's a negative, and then it's a negative, and then it's a positive. So your 3 intervals, so you have your intervals there, or 4 intervals really, test, and then sign. So going from negative infinity to negative 2, negative 2 to 0, 0 to 2, and then 2 to infinity. Testing numbers like, so at negative 3, we got a positive value. At negative 1, we have a negative value. At positive 1, we have a negative value. And at 2, we have a positive value. We can see at negative 2 and 2, we change signs. At negative 2, we go from positive to negative. We go from increasing to decreasing, which means we have a maximum at x equals negative 2. Whereas at positive 2, we go from decreasing to increasing because it's minus to plus. That means we have a minimum. at x equals positive 2. But at 0, there's nothing. It's not changing. It's going decreasing and still decreasing. So 0 is not a min, nor is it a max. You do need to be very careful with the graphs. We're going to spend an entire section on this, 5, 6, analyzing just simply graphs and talking about this a bit further. Because obviously, intuitively looking at this going, well, wait, there's a maximum point at 0, 0. There's a minimum point at, like, negative 1.5, negative 4, or positive 1.5, comma, negative 4. Like, those are, like, minimum points there. But again, this is the graph of the derivative. They're talking about the original function f of x. They're going backwards. So when you're going backwards, you're looking at where is the derivative positive and negative. That's where the original function is increasing and decreasing. That's the key for that kind of stuff. All right. Sometimes they'll give you you get the derivative right from the beginning. That's what we have here. We're given f prime of x equals x cubed minus 6 cosine of x squared plus 2. So we don't have to take a derivative. And questions in textbooks or in AP like doing this to make you do a more interesting question without having to go through a crazy process of taking the derivative. Because the derivative of how to get here, so like anti-deriving this, would be quite spectacular. Now, to graph it, to solve this, you're going to have to graph it. So we go ahead and type this information to our calculator, making sure, again, it's in radians mode because there's a trig function here. You should always be in radians mode for anything in calculus, quite honestly. And your graphing screen on the usual negative 10 to 10 window should look something like this. Goes up, down, up. It looks like that curve right there. And this is, again, the graph of f prime of x, which means these 3 locations are your critical points. And those 3 locations are going to be, let's see, this first one, when you do your second trace calculated to 0, is negative 1.922. The middle one here is negative 1.250. And this last one here is a positive 1.018. So we take a look at our interval chart. So our interval, test, and then sign. We know from negative infinity to a negative 1.922, negative 1.922 to negative 1.250, and then negative 1.250 to 1.018. And then 1.018 on to positive infinity. So we test like negative 2, negative 1.5, 0, and 2. We can see at negative 2 we are below the x-axis, which means the derivative is negative. At negative 1.5, that little peak in there, we can see we're above the x-axis, so the derivative is positive. At 0, we can see we're below the x-axis, so the derivative is negative. And at 2, we can see that we're above, so it's positive. So this means that we've got a minimum when, again, we go from decreasing to increasing, which would be at the negative 1.922 and at the 1.081 because we're going from decreasing to increasing there. Whereas we got a maximum when we go from increasing to decreasing, that's occurring at the 1.250. All right, so again, the graph can be very helpful for this kind of stuff, especially when you're given just a derivative and it's an ASCII equation like this. You really can solve this one algebraically. The key is you'll know when you really shouldn't be using a calculator because you'll be told not to directly, or it's based on a question that's very easily solvable without a calculator itself. All right, so all that is the first derivative test. Now, it's not the only way to determine whether you have maximums or minimums. You still need to do the first derivative equal to 0 to find the critical point. That's never going to change no matter what test you use. But we also have what's called the second derivative test. So for the second derivative, you're still using the same critical number. So we're not doing the second derivative equal to 0. It's a common mistake. It's still first derivative equal to 0 to solve for the critical point. But then we plug that value into the second derivative. And if the second derivative is positive, well, then it's a minimum. If the second derivative is negative when you plug in that point, then it's a maximum. And unfortunately, if the second derivative is equal to 0, it fails to exist, then the second derivative test fails, and you have to use the first derivative test. So obviously it has some disadvantages. Typically, I will only ever use the second derivative test if it's a very simple polynomial function, because then it's easy to plug. It's easy to take a second derivative and solve it from there. Or if I have a nasty first derivative equation and I have to solve it using a calculator, then I can use my n-deriv tool to then find the value of the value of the derivative of that function right there. It kind of depends. So this would be the example of a simple polynomial where it's best to just do the second derivative to find the equation, the value. So our first derivative is 4x cubed minus 4x squared equal to 0. We factor out, 4x. We factor out our 4x, leaving x squared minus 1. So 4x equals 0 when x is 0. X squared minus 1 is equal to 0 when x is plus or minus 1. So -1, 0, and 1 are our three critical points. So we could do a first derivative test, but we're going to do the second derivative test here. It's simple enough. So our second derivative would just simply be 12x squared minus 4. And what we're going to do is we're going to plug in those critical point values, -1, 0, and +1, and see what we get for the second derivative. So 12 times -1 squared minus 4 is a +8, which means since it's positive tells us we have a min, so we have a min at x equals -1. Plug in 0. We get a -4, which means we have a maximum. So we have a max at x equals 0. And then we plug in +1. We get +8, so again, it's also a minimum. So as you can see, it's very simple with a simple polynomial equation. Nothing too fancy about how we can solve that one out. So good idea to use the second derivative test here. Now this one's a trig function, but it's a simple trig function. So this is also, again, probably a good bet, even without the directions how you use the second derivative test, to use the second derivative test here. So our first derivative, that's root 2x, so it'll just be root 2, because it's a linear, so whenever it's linear, it's always just the coefficient in front of x. Cosine becomes negative sine, it's already a negative, so it's plus 2 sine x. Set that equal to 0, so we get 2 sine x equals negative root 2, so sine x is a negative root 2 over 2. Now, as always with the trig derivative, solving for a critical point, you need to be given a range of values to work with, because the trig goes on infinitely. So 0 to 2 pi is just your unit circle, so where on the unit circle is sine a negative root 2 over 2? That's going to occur at 5 pi over 4 and 7 pi over 4. And again, rather than doing a first derivative test where you set up intervals and see increase and decrease and all that, this is a simple enough equation, I can just take my second derivative. So now the root 2 disappears because there is no x. Sine becomes cosine, I get 2 cosine x for my second derivative. So we go ahead and plug in 5 pi over 4 into the second derivative, and we plug in 7 pi over 4 into the second derivative. So 2 cosine of 5 pi over 4 is 2 times a negative root 2 over 2, which is negative root 2, which means we have a maximum at x equals 5 pi over 4. Whereas when I plug in 7 pi over 4, cosine of 7 pi over 4 is a positive root 2 over 2, so the 2's cancel, leaving positive root 2 for the value. Since it's positive, means we've got a minimum at x equals 7 pi over 4. So that's how we're using our second derivative test. For most questions, besides obviously for my students for questions in like the homework or the quiz, but in general, you'll never be told to use one test over the other. It'll be kind of your choice. And again, like I was talking about, if the equation is a simple equation to take a second derivative for, second derivative test is a good idea. If it's overly complicated, it was a chain rule to begin with, so now it's even more complicated chain rule, probably a product rule, then second derivative might not be the best bet. If it was from a quotient rule, just in general, if the equation is complex, it's not really your best strategy. So when it's a simple one, good idea. If it's the one area where being overly complex might still be to your advantage is if you're allowed to use a calculator to calculate numerical value. Because if I have the derivative, so if I go back for a second to this thing right here, this would have been an overly complicated function to work with. What we could do is you could do your numerical derivative. So I go to my calculator, I do my math and deriv for this equation, x cubed minus 6 cosine of x squared plus 2, and I tell it to do it at the value of negative 1.922. And it's going to give me a positive value, a positive 23.18645,002. Positive means min, which we already said it was. So that's one other area where the second derivative test might be to your benefit. It just, again, entirely depends on what you want to do with that. All right, so that's our test for Extrema. Up next, We'll be talking about, just again, talking more about these intervals for increasing, decreasing. Also talking more about the idea of whether or not we have an absolute max or an absolute min. So these are all relative max and mins. We got to take a look at the highest actual point or the lowest actual points. All right, so I'll see you next time for that.